Hi, welcome to another data science video. The previous video about hypothesis testing shortly introduced p-values. Here we'll go much deeper. Why do we need p-values? Well, they help to make decisions and answer the question whether we found something new or not. But despite the fact that p-values are actually useful, they are far from perfect. And while everyone uses p-values, understanding them and using them correctly is very hard. The definition of the p-value from the book is often correct, but rarely intuitive. Intuitive explanations are often not entirely correct. So in this video, we'll start with an intuitive definition and we'll gradually build up our understanding of the p-value step by step. Thus, I don't recommend to skip any part of this video. We'll also talk about how to use and interpret p-values correctly in order to make better decisions and better science. The most intuitive explanation of p-values I have found came from Andrew Wickers. P-value is the probability of the toothbrush being dry if you've just cleaned your teeth. Let's start with that. So the P stands for probability, and it refers to the probability that we would have gotten the result we did just by chance. Let's have an example. If you throw a fair coin, you have only two possible outcomes, heads and tails. The chances to get tails are 50%, clear and boring result. The chances to get two tails in a row are 25% because we have four possible outcomes. It's actually pretty likely to get two tails in a row, so nothing unusual here, the coin must be fair. However, three tails in a row starts to feel strange, and we start to doubt whether the coin is actually fair. And if you get six tails in a row, despite only 1.5% probability to get them, the null hypothesis that this coin is fair would seem ridiculous, and you'll reject it because it's simply too unlikely to happen randomly or by chance. Wait a second, let's get back and see what we just did. This example, which defined the p-value as one particular probability of having only tails, is clear, intuitive, but only one-sided. It isn't wrong, but one-sided p-values coming from only one probability is not what people use. The real p-values are two-sided. Then why did we learn about one-sided p-values at all, you might ask? Well, it was totally necessary for a better understanding of the second definition of p-values. And this is actually one of those definitions from the book where people start to run away from statistics. Namely, p-value is the probability to get the data we have collected as extreme data or more extreme data just by chance, assuming our null hypothesis is true. In our first coin example, the probability of having two tails in a row is 25%, because there are only four equally possible outcomes after flipping a coin two times. These four possible outcomes is our distribution. And the data we have got, namely two tails, is the first of the three probabilities we need, and is only one side of the distribution. The second side of this distribution would be two heads, which are as extreme as two tails and are the second part of the three probabilities we need. The probability of getting two heads is also 25%, and we simply sum up both probabilities. Now we have a two-sided probability, but the complete p-value needs another part. The third and the last part of the p-value is the probability of observing something rarer or more extreme than our data. In this case, it is 0, because no other outcomes are more extreme than two tails or two heads. Thus, if we add this 0 to the probability of having either two tails or two heads, we'll get a final p-value of 0.5. Thus, the p-value is the probability of getting the data we collected, which are two tails, as extreme data, namely 2 heads, and more extreme data, which is 0 in this example. Now, let's throw our coin another 2 times and calculate the p-value to get 3 tails and 1 head. The null hypothesis would be that our data, 3 tails and 1 head, is nothing special, but belongs to this exact distribution. 4 out of 16 possible outcomes would have 3 tails and 1 head. That would be our data, and with that, the first part of the p-value. The data, which is as extreme as the data we are interested in, is 3 heads and 1 tail, which will be the second part of the p-value. 2 out of 16 possible outcomes are more extreme than our data, namely 4 heads and 4 tails, and are the last part of our p-value. Adding them all together would result into a p-value of 0.625. So we would fail to reject the null hypothesis that our data is nothing special and would need to conclude that 3 tails and 1 head belong to this distribution. Calculating a p-value from discrete numbers is kind of easy, but how do we do it for continuous numbers? Plotting our discrete data will help to understand that. If we plot our values from the last example, we would find the most probable outcomes in the middle, a bit less probable on both sides of the middle, and finally the least probable values very far away from the middle. This will become the probability distribution of our discrete values. We can also cover plotted values with a curve to better visualize the distribution. Now, if we mark our discrete values with discrete numbers on the x-axis, we'll see that we'll be able to add any continuous value in between those discrete numbers. For example, 0.3 or 0.5. And for every of these continuous values, we would be able to calculate probability in the exact same way as we just did for 2 tails or for 3 heads and 1 tail. That's how we arrive at the continuous probability distribution. Interestingly, the p-values for such continuous probability are also calculated in the same way. But instead of adding only 3 discrete probabilities, namely our data as extreme data and more extreme data, we add up only 2 discrete parts, our data and similarly extreme data, and 1 continuous part, more extreme data from both tails of the distribution. And since we calculate probabilities of many points under the curve, and add all of them together or accumulate those probabilities under the curve, we'll get the area under the curve, which then is our p-value as a cumulative probability, including all the values which are as extreme or more extreme than our data. An example of such curve could be the weight of people. For instance, the average weight of a German male is 80 kilos, with 95% of them weighing between 70 and 90 kilograms. By the way, these numbers are totally made up. 2.5% of them will weigh under 70 and 2.5% will weigh above 90 kilograms. If we get a new data point, namely a weight of a new person, we can calculate the p-value for that point. Our null hypothesis is that this person's weight is not different from our distribution. If this person weighs 75 kilograms, the area under the curve, or p-value, which includes all the values as extreme or more extreme than 75 kilograms, will be 0.6, which is fairly big. So we would fail to reject the null hypothesis, concluding that the person could be a German male or is at least not different from German males. However, if the weight is 65 kilograms, the area under the curve is quite small, around 0.02, Here we can reject the null hypothesis and conclude that this person must belong to a different population, for example, women or a man from a different country. So we see that the p-value goes from 0 to 1 and is a continuous number, which corroborates with the last definition we have, the original definition of Ronald Fisher. A p-value is an index measuring the strength of evidence against the null hypothesis. This strength of evidence can be intuitively explained as a measure of similarity. For example, if two samples are identical, there is 100% similarity and 0% difference. So our p-value is equal to 1. If similarity is only 60%, then the difference is 40%, which is much bigger than 0, but is still small. But if the similarity drops to 5% or below, then the difference of 95% is often considered significant. And we can confidently reject the null hypothesis that there is no difference between our samples in favor of our alternative hypothesis that such difference exists. So, as we have learned, the first three definitions say that a p-value is a probability, which is a number from 0 to 1, and the last, Fisher's definition, says that a p-value is an index, which is also a number from 0 to 1. But wait, does it make any sense to dichotomize a continuous number from 0 to 1 into only two categories, significant and not significant? Of course not. The p-value is not black and white, but everything in between, like 50 Shades of Grey. Oops, sorry, not that 50 Shades of Grey, that one. But if dichotomizing continuous p-values into two categories, significant and not significant, doesn't make much sense, why is the whole world doing exactly that? Well, the basic explanation is neither philosophical nor scientific, but sociological. Everyone uses them. To better understand why the whole world dichotomizes them, we need to briefly explore the history of p-values. Ronald Fisher, the father of modern statistics, saw the p-value as an index measuring the strength of evidence against the null hypothesis. Fisher himself proposed if the p-value is above 0.1, there is a weak evidence against the null hypothesis, so that we cannot reject it. If, however, the p-value is below 0.02, the evidence against the null hypothesis is strong. Fisher sometimes used the threshold for the p-value of 0.05 himself to reject the null hypothesis, but without any clear reason. Moreover, he recommended to treat a p-value around 0.05 as inconclusive, where we'd need to repeat the experiment or collect more data. But if we insist on making a conclusion from hypothesis testing, we can make two types of mistakes. The first mistake is called a type 1 error, and the reason Fisher used p-values at all was to reduce the probability of the type 1 error, which is the probability to find something what is not there. For example, that somebody has cancer while being totally healthy. Type 1 error is also sometimes called a false positive. The most typical type 1 error happens when we measure a difference between two groups and find this difference to be significant, while both samples came from the same population. Having a stiff threshold of 0.05 can be good because from all the null hypotheses you test, in the long run you will falsely reject at most 5% of correct hypotheses. But it is also bad because it statistically guarantees that 1 in 20 healthy people will have cancer just by chance, or in 1 out of 20 statistical tests will find nonsense just by chance. Thus, lowering the p-value to, let's say, 0.01 reduces the probability of finding nonsense. But doesn't mean that any threshold is evil. Well, no. The threshold of 0.005 means that if there is no difference between group 1 and group 2, and if we did this experiment 100 times, that only 5 of these experiments would result in a wrong decision. This would be 5 false positives, or 5 times type 1 error. Lowering the threshold to, let's say, 0.001 would reduce the number of false positives to 1 out of 1,000 experiments, but the costs of doing 1,000 experiments are often much higher than it is worth. Along the type 1 error, Newman and Pearson also advocated the type 2 error that could be made in interpreting the results of an experiment. The type 2 error is the probability to miss something what is there, often called a false negative. For example, failing to find cancer when cancer is already in the body. Newman and Pearson's idea of hypothesis testing was actually really good because it's supposed to reduce the number of mistakes by keeping the rates of both type 1 and type 2 errors low. However, only the easy part of their approach, that the null hypothesis can be rejected if the p-value is below 0.005, has been widely adopted and stuck in the medical research, causing the current dichotomy of results into significant and not significant. Two serious consequences of this are that potentially clinically important differences observed in small studies are denoted as not significant and ignored, while all significant findings are assumed to result from real treatment effects. Well, how do we deal with type 2 errors? Increasing the sample size will increase the power of the experiment and therefore it decreases the probability of type 2 error. So now we know that hypothesis testing can produce two types of mistakes. The type 1 error is an error because p-values help to maintain nonsense, while the type 2 error is an error because p-values help to miss something important. Therefore, we should stop dichotomizing our results into significant and not significant. But if after all this you still want to continue dichotomizing your result into significant and not significant, please answer the following question. Is the difference between a p-value of 0.051 and 0.049 statistically significant? The answer is a clear no. However, if using a p-value continuously totally blows your mind and you still need some pragmatic decision-making tool, consider using a hybrid approach which singles out 5 instead of only 2 categories on the strength of the evidence against the null hypothesis in favor of the alternative. If the p-value is above 0.1, the data shows no evidence against the null hypothesis. P-values between 0.05 and 0.1 show weak evidence against the null hypothesis. It is sometimes reported as a dot and called a tendency or a suggestive result. P-values between 0.01 and 0.05 show moderate evidence against the null. It is sometimes reported as 1 star. P-values between 0.01 and 0.001 show strong evidence and could be reported as 2 stars, while the p-values below 0.001 indicate a very strong evidence against the null and are often shown as 3 stars. Having these 5 categories, you will free yourself from the necessity of using the cutoff of 0.05. And in fact, from the necessity of using any cutoff at all. And here is why. The cutoff itself is up to you and is highly dependent on the experiment. It might sound fuzzy, but it actually gives you freedom to adjust your decision-making process to reality. Let's have a look at 3 examples. Imagine you study a new treatment for a deadly disease, and your p-value for the difference between control and treatment groups is 0.15. If you strictly follow the 0.05 cutoff, you'll fail to reject the null hypothesis and would conclude that there is no difference between the groups and that the treatment does not work. The p-value of 0.15 makes you only 85% sure that such difference exists, making this difference not significant enough. However, if you don't blindly follow the cutoff of 0.05, you could look at this experiment in a completely new way by saying, I am 85% confident that new treatment works and that we found a new way of treating a deadly disease. Similarly, if I was 85% confident of winning the lottery, I would definitely play. But if I strictly follow the cutoff of 0.05, I would be not confident enough that I will win, which is ridiculous, and I would not play. On the opposite side, if an airline company welcomes you aboard with the catchy phrase, "We are 95% confident that you'll survive, so your probability of crashing with us is below 5%, would you go aboard? I personally would run away. The airline company would chase me though and scream, "Stop running away! We successfully rejected the null hypothesis that you will die." But I would only be willing to fly if my level of confidence in my survival increases to 99.9999%, or if my chances to die would become 1 to a million flights. So you see, the freedom to set up your own level of confidence, or the cutoff, depending on the situation, makes you a better scientist, while blindly following the cutoff of 0.05 would either keep you poor or just kill you.
The dramatic effect here serves only for educational purposes, while hoping to significantly increase the probability that you'll remember the material.
If you want to know what a lot of statisticians think about p-values, you could read this article of the Wasserstein from 2019. Here I would just reduce this article to some recommendations of what to do and what not to do with p-values. These recommendations would first enable you to find fewer false positives, or in other words, to make fewer type 1 errors, and secondly, will help you to overlook fewer discoveries, or in other words, to make fewer type 2 errors. Report precise continuous p-values without reference to arbitrary thresholds. For example, p is equal 0.02 rather than p is below 0.05. Lower the 0.05 significance threshold for claims of novel discoveries to 0.005 threshold, especially for large studies, and refer to p-values between 0.05 and 0.005 as suggestive. Look for both a small p-value and a large effect size before declaring a result significant, instead of dichotomizing p-values alone. Produce solid data, supplement p-values with visualizations of confidence intervals, justify sample size and statistical methods used, use more of the non-parametric, robust or non-linear methods, always check assumptions and use different data analysis techniques for the same hypothesis. Most importantly, reduce unplanned and uncontrolled modeling or testing, also known as p-hacking, because examining 20 associations will produce one significant result by chance alone. Thus, testing multiple variables, using long questionnaires with hundreds of variables, and measuring a wide range of potential outcomes would guarantee several false positive findings. A solution for that is, again, to reduce the threshold. And that's what Bonferroni correction does. What not to do? Don't dichotomize p-values into significant and non-significant based solely on some arbitrary threshold, such as 0.05. Remember, a p-value is not black and white. P-value is 50 shades of gray. Don't treat p of 0.051 and p of 0.094 as being different. The difference between significant and non-significant is by itself not statistically significant. So don't discard a well-designed, excellently conducted, thoughtfully analyzed and scientifically important experiment only because it failed to cross some strange threshold of 0.005. For example, if you get a p-value of 0.009. Don't believe that your p-value gives you probability that your test hypothesis is true. P-value is the probability of the data, not of any hypothesis. There are of course many more do's and don'ts in this article, so feel free to explore it yourself. Here I just would like to say that most of the scientists can't tell you what the p-value is. Most of the statisticians can, but they can't explain it properly. So don't give yourself a hard time if you're still a bit confused. It's normal. Instead, I'd suggest we stop caring about understanding the p-value but start to use it properly. Because we don't need to understand how the car works, we only need to know how to drive. Thank you for watching.